Okay, so we are going to look at a little mini lecture on air resistance. I'm sort of in a makeshift learning glass resistance studio. So you'll have to deal a little bit with the traffic behind me and the trees up above and all of that. All right, so what is this idea of air resistance? All right, I'm going to task you with something first. Let's imagine that I have a book and a piece of paper. And I'm going to drop them from the same height, let go at the same time. Which one's going to hit the ground first? Chances are you said the book. So, wah, wah, the paper hit the ground first. All right, I won't put the paper under the book. If I drop the piece of paper and the book at the exact same time from the same height, which one's going to hit the ground first? Chances are you said the book again. And wah, wah, the book and the paper hit the ground at the same time. All right, I won't cheat. If I let go of the book and the paper at the same time, of course, the paper falls much slower than the book. Well, why is that? That, of course, has entirely to do with air resistance. So what is air resistance? What causes it? What is going on? Well, we know a couple things, probably intuitively, that air resistance is a force. And it's a force due to the molecules of the air interacting with the object that's falling through it. Molecules, air molecules, of course, are things. They're things, they're particles. And so as particles hit the object, hit the book, hit the paper, well, they interact. And we know that anytime something interacts, we have a force. So due to the fact that the molecules are interacting with the object, of course, causes this force. Well, what's air resistance dependent on? Are there things we can change about the object or the air that it's interacting with to influence the amount of force that the object feels? Yeah, and we're probably pretty intuitive about it. Let's imagine, I like to use an analogy of being at a party. Let's imagine you're at a party, and for some reason you're carrying a really big book through the party. Like, take this 10 times the size. And there's a lot of people at the party, and you want to kind of walk through the party. Well, you're better off walking through the party like this, or with your book like this. Well, you're going to run into a lot less people if you walk with your book like this than if you walk with your book like this. A lot more interactions with this orientation than with this. Well, what's the difference? The surface area. So we probably already knew that surface area plays a role in the amount of air resistance we have. Okay? So if I increase the surface area, I increase the air resistance, and we're going to use the capital letter R to indicate the force caused by that air resistance force. All right, well, what else influences the air resistance? Let's imagine we're walking through our party, and we're going to use the larger surface area to get that impact. We're walking through the party, and it's a pretty lame party, so people start leaving. Well, as people start leaving, as you're walking through, you're going to run into less people. If there's less people around, there's less chances for those interactions. Less interactions, less overall force. All right, so how does that relate to the air? Well, that has to do with the air density. So the density, the amount, a number of air molecules in a certain volume. Well, if I increase that, if I have a lot of air molecules, well, then I'm going to have a lot of interactions. If I decrease that, if the party's lame, a lot of people leave, well, I'm going to have fewer air molecules. So as I increase density, we use the Greek lowercase letter rho, then I increase my air resistance. Okay. What else might have an influence? It's all about the number of interactions that happen. How can I get even more interactions or less interactions if I'm walking through this party? Well, in a certain amount of time, if I walk through the party, I have so many interactions. If I run through the party, well, then I'm going to have even more interactions. As I move faster, I'm going to run into more things in that same amount of time. So the last real critical piece is our velocity. So as I increase the velocity, I increase the amount of interactions I have in a given amount of time. I increase the air resistance. And actually, velocity has a big impact. It's related. The air resistance is proportional to the velocity squared. So even small changes in velocity cause big changes in the amount of air resistance that happens. All right, a lot of those are probably pretty intuitive when you think about what is going to influence an object falling through the air. The area, the surface area of the object, that's interacting with the air, the density, how many molecules it can interact with, and then how many molecules it interacts with over time, the velocity. We have some experience with this even when we're not falling through the air. So imagine how easy it is to run when it's not windy outside. But as soon as it's windy outside, well, now the velocity of you relative to the air molecules has increased. And it's harder. You're resisting, you're all struggling with that wind. So that's an example that's sort of personal with air resistance. All right. We're not going to worry about the equation for this class. I just want you to think about the conceptual ideas of air resistance. And I also want to think about an idea of what happens, getting back to our question of, well, what if I drop the book and the paper at the same time? Air resistance is the thing that's causing the paper to have a different experience than the book. But why do they hit the ground at the same time? We've done a lot of kinematics where things are in free fall. They hit the ground at the same time. We witnessed that in class. So how is it that when I take a much more extreme example, that air resistance influences how long it takes an object to hit the ground? Well, we're going to use our conceptual usage of free body diagrams to answer that question. So we're going to look at a free body diagram of the book and of the paper. So let's think about what are the forces interacting on the book and what are the forces interacting on the paper the instant I let go. So right as soon as I let go of the book and the paper. Well, we know that the book experiences a force of gravity, and that's between the book and the earth. And of course, we also know that the paper experiences a force of gravity, and that's between the paper and the earth. So if I go to draw my free body diagram, and we're going to just say this is at the start, and at the start. So instant I let go. If I draw my free body diagram of each of these two objects, how does the force arrow, force of gravity, compare between the book and the paper? Well, we know that the force of gravity is equal to the mass times g in both cases. And the book is a lot more massive than the paper. So the force of gravity on the book has to be a lot larger than the paper. G is the same. That's our acceleration due to gravity. That's constant. But the book has a much larger mass. So if I were going to draw the force of gravity arrow of the book, it has to be larger than the force of gravity arrow of the paper. I'm drawing those relative to one another. All right. And we also know we're no longer in a vacuum like we've been assuming. We also know that the air is causing an interaction as soon as I let go on the book and the paper. And really in the very, very, very first little bit of the movement, we have very slow movement, so the velocity contribution is very, very tiny. And the air resistance is made primarily of the area contribution and the density contribution. So if I think about the book and the paper in this situation, how do those two things compare? Well, the book and the paper are the exact same size. And so the area contribution of air resistance for both of them is the same. And, we're outside, so the air, and they're in the same spot, the density contribution for both of them is the same. So if I think about the air resistance, right at the instant I let go of the book and the paper, the amount of air resistance on the book and the amount of air resistance on the paper are the same. So I'm going to draw my air resistance arrow. They should look the same for both the book and the paper right at the start. Okay, now let's use that conceptual logic model to see what's going to happen to these two objects after I let go of them. We know that the net force for both of these two objects, the net force, is in the downward direction. So the sum of the forces is in the downward direction for both of these two objects. Well, that's because the downward arrows are bigger than the up arrows. If the sum of the forces is in the downward direction, then the acceleration is in the downward direction. If the acceleration is in the downward direction, and we know the object is starting from rest and then moving in the downward direction, it's speeding up. So I see an increase in velocity in both of these. All right. Now, how does that increase in velocity affect the air resistance? Well, it increases it. So let's look at the free body diagram after a little bit. All right. Well, the force of gravity of the book that hasn't changed because, of course, the mass of the book hasn't changed. And the force of gravity of the paper, that hasn't changed because the mass of the paper hasn't changed. I still have my air resistance contribution due to the size, the area, and the density. It hasn't changed either. But now the object's moving, so I have a velocity contribution to the air resistance as well. So I'm going to just add that on top so that this whole thing is now capital R. Erase the black one, and now that whole thing is capital R. Okay. The black part of that arrow is representing the contribution of the air resistance, the surface area and the density, and the red part of that arrow is representing the contribution due to how fast the object is moving. Okay, well now let's use our logic model. The net force for the book, well, up arrows are still smaller than the down arrows, so the sum of the forces is in the downward direction. And that means the acceleration is in the downward direction. And it's moving in the downward direction, accelerating in the downward direction. That means we're increasing our speed. In the case of the paper, well, the up arrows, well, they're still smaller than the down arrows. So the force, net force, is down. That, of course, means the acceleration is down. And since it's moving down, acceleration is down, we're increasing our speed. Okay, so both objects continue to speed up. Now let's go a little bit further. Let's say that's even more later. All right, so both of these objects have now sped up. We'll draw our free body diagram again. Our force of gravity due to the book hasn't changed, the mass hasn't changed, and the force of gravity on the paper, well, that hasn't changed either because the mass hasn't changed. We still have the same contribution from air resistance that we had due to the density and the area, and now it's moving even faster, so my contribution to air resistance for the velocity is going to get bigger. And this whole thing is my air resistance. So let's do the logic model. Well, my up forces are still smaller than my down forces. So the sum of the force for the book is down, therefore the acceleration is down, and we're going to get an increase in that velocity. The sum of the forces on the paper, well, they're the same. So the sum of the forces are equal. The sum of the forces are 0. The net force, the ups and the downs are the same. Well, if the ups and the downs are the same, that means that there's no acceleration. And if there's no acceleration, there is no change in velocity. Now the object was moving, so it keeps moving. But it moves at a constant. Now that object, the paper, just falls to the ground at a constant rate. If it falls to the ground at a constant rate, well, then the air resistance doesn't change. We still have the same contributions that haven't changed. Force of gravity we know hasn't changed, and it just continues to fall at that constant rate. But what happens to the book? Well, it's sped up. So now it's moving faster than the paper. And if it's moving faster than the paper, it's going to get where it's going a lot sooner than the paper is. And so it reaches the ground first. As it falls to the ground, this air resistance arrow continues to build. And at some point, not before it hit my makeshift table here, which is my ironing board, but at some point, the air resistance arrow will build enough due to the contribution due to the velocity that it will match the force of gravity on the book. And when it matches the force of gravity on the book, we'll know the net force is 0, acceleration is 0, no more change in velocity, and that book continues to fall at a steady rate. All right, so using our logic model, we've actually developed this idea that we know as terminal velocity. Terminal velocity is the speed at which an object is falling that the air resistance on that object matches the force of gravity, and therefore there's no more change in velocity. So we've probably heard about that term before. If I change the surface area of an object, I'll change its terminal velocity because my contribution, represented by the black arrow, is going to change. And therefore, it might take more contribution of the velocity to reach equilibrium if I have a smaller surface area, or less contribution of the velocity to reach equilibrium if I have a larger surface area. Okay, so that's the idea of terminal velocity that I want you to be thinking about. purely in a conceptual framework. There are some practice problems for you to try, and good job.